So, good morning everyone. Today we will start with the FIR filter designing. So, before we go into the details, we need to understand certain rules and certain properties of the FIR filters, which will be helpful for us in the what do you call in the coming classes. Okay. So the first of all is that we need to understand certain considerations. And what are these considerations? The first consideration is that while designing any FIR filter, we will take the modulus of h of omega, that is the amplitude response equals to 1. Okay. So what is the implication of this one? The implication of this one is that if you see h of modulus of h of omega, what we have discussed that h of omega, it can be given by y of omega divided by x of omega, right? So if we use this formula and rewrite this equation, we get y of omega divided by modulus of y of omega divided by the modulus of x by x of omega, it is equal to 1. So what does that mean? This means modulus of y of omega is equal to modulus of x of omega. Okay, that means there is no loss of the no loss of the signal frequency component. That means if you have designed a filter, so what would happen? Whatever frequency you would be liking to reject, those frequency will be rejected. Otherwise, other frequency components, they remain unhampered. Okay, they remain unhampered. So many students ask that, sir, why you have taken 1? Why not 2? Why not 3? Why not 4? Right? So you need to understand, then when we talk about filter, conventionally the filters are designed to reject some frequency components. Okay, it may be a single frequency component or it may be a band of frequency components. So in other words, you can say the filters, they allow certain frequency components to pass through and it suppresses some other frequency components, right? But the filters are not meant to induce some gain into the signal. Okay, filters are not meant to induce some gain to the signals. Okay, so while designing the filters, we keep that in mind that the filters, they will not have any gain. Okay, so herein accordingly we choose this value of 1. Okay, now coming to the second point, it says direct process. What do you mean by direct process? It means that if I want to design a low pass filter, then using the FIR filter designing method, I directly design the low pass filter. If I want to design a band pass filter, I will be designing a band pass filter. If I want to design, say, band reject filter, okay, or band stop filter, band reject filters, they are also regarded as band stop filter. So we can directly design it. Say if I want to design high pass filter, I can easily design the high pass filter or even the notch filter, whatever. So whatever the filter you want to design, you can design that filter directly by the FIR filter designing technique. On the other hand, in IR filters, what happens is that what I told you that we take the information or the knowledge from the analog domain and then we try to replicate that into the digital domain, right? The same thing happens over here also. So in the analog domain, designing of the low pass filter is very easy. Okay, so while designing the IR filters, we initially design a prototype low pass filter. Okay, with a prototype low pass filter, where the cutoff frequencies, the roll off, and all these things, they are decided over there. Okay, all the characteristics, what should be the characteristics of the pass band frequency response, what should be the characteristics of the stop band frequency response, and all these things. And then we go for the frequency transformation method to convert the low pass filter either into the low pass filter or into the band reject filter or into the band pass filter or into the high pass filter, etc. So you can see over here in IR filter, it is an indirect method of designing the filters. We initially design a low pass filter and then we apply certain frequency transformation methods to convert those filters into desirable filters. Okay. Then third, individually and separately. So say for example, I want to design a band pass filter. I can design a band pass filter as per the given specifications. And if I want to design a low pass filter or a high pass filter of similar configuration, I can design those separately and I am good to go. Okay. So the FIR filter designing, this gives us the flexibility to design all the filters in an individual manner or in a separate way, whatever way you want to do, and then you can do the cascading or you go for the parallel implementation of the filters, whatever you want. So that is there. Now the fourth point, it is an important point and it is related with the first point to a certain extent. Now what is that? But this is one of the most important point of the FIR filters. So h of omega, if you look into the polar coordinates, if we look into this, so we give it as capital M, which is the magnitude of h of omega multiplied by e to the power minus j omega n. However, if you see this magnitude, we are told that it is 1. So we can write h of omega, it is equal to e to the power minus j omega n. So what is that? It is nothing but e to the power minus j theta. What is theta? Theta is the phase component of any given system, right? Now we have seen that phase of h omega, from the first equation we can see that phase of h of omega, it is equal to theta, but I have over here I have written theta omega. Why? Because phase is also dependent on the frequency. Now why it is dependent on the frequency? Because when you design any filter, if you see whatever filters you are designing, you are having certain number of poles, certain number of zeros. Suppose this angle, this is minus of omega t. If I place another pole, it will be minus omega t, minus of omega t. Okay, because for this thing, for these poles, dual poles, it will be, the phases will be the same, and it will become minus of 2 omega t. But we have this zeros also. So zeros will be having say for example theta 1 minus of 2 omega t, something like that, right? So if I change this thing, for this poles minus of 2 omega t, it will remain same because omega has changed. Say now it becomes omega 1, but the value of frequency has changed, that's why it is changing, but the expression remains the same, minus of 2 of omega 1 t, say for example. However, for this 0, the theta would be different again, right? So the theta will be different again. So if you see, as the frequency changes, as we are going to different frequency components, the phase is changing. Now since the phase is changing, that means it is dependent on the frequency component. It is dependent on the frequency component. Okay. So that's why I have written that phase of h of omega, it is equal to theta omega. Now what does that mean? If we compare this theta omega and over here these two equations, we get theta omega is equal to minus of omega n, okay? Minus of omega n. And what is this n? This n, it is regarded as this time factor. This is regarded as the time factor. Okay. Now from here, your tau p, which is regarded as the time delay, it is given by minus of theta omega by omega. Minus of theta omega by omega. However, if we take a derivative of this one, this factor, okay, minus of d theta omega by d omega, then it is regarded as the group delay tau g. Okay. Now in the case of FIR filters, this tau p and tau g, they are constant and usually they vary linearly, and because of this reason we say that the FIR filters, they are usually constant phase filters, and this is an important property of the FIR filter. Now what does that mean? This means, suppose I am having a signal. So I am having T and it is repeating. I have just drawn a single cycle. Okay. So this is, sorry, sine of 2 pi f1 t. Now suppose this signal has been delayed. Delayed by how much? Delayed by tau. Okay. Now it is starting the same thing. It is starting its own journey. Okay. Now the thing is that what is happening over here? So this signal, it would be given by sine of 2 pi f1 t minus tau. Okay. Say for example, if I extend this signal component, okay, and I look into this 0, so what happens? This component, it would become minus of 2 pi f1 tau. Okay, because at this point t is equal to 0, right? So minus of 2 pi f1 tau. Okay, what is this? I have gone back, so it is nothing but minus of pi by 2. How much I have shifted? I have shifted by a factor of minus of pi by 2. Okay. Then say for example, I have a signal. I have a signal which is composed of two sinusoidal signals. Say for example, F1 and F2. F1 and F2, where F2 is equal to 2 of F1, where F2 is equal to 2 of F1. Now let us see the thing. So what happens? Now within this one cycle of the previous one, I am having two cycles. Now again let us delay this thing by the same format, like this. Now if I have to go to the time equals to 0, so what happens now to this equation? It becomes t is equal to 0. So we have this frequency component as minus of 2 pi f2 tau is equal to how much phase shift has been there? The phase shift is minus of pi. The phase shift is minus of pi. So from here if you try to find out tau, for the first case it would be 1 by 4 of f1, and in the second case it would be equal to pi cut here 1 by 2 of f2. Okay, so what is 2 of f2? One by 4 of f1, right? So what phase, the change of the phase, what is happening with the frequency, it remains the same. And why it is called linear phase response? It is regarded as the linear phase response. Suppose you are having two frequency components f1, f2. Again f2 is 2 of a, so we are having say pi by 2, we are having pi. So for f1 was this thing, draw a line, there would be a straight line, this would be a linear, this would be linear. Okay, this would be linear. Now you go back, now you go back over here, it said constant phase filter, okay, or a linear filter. Why? Because tau p and tau g, which should be a constant. So if you see tau p, we just calculated tau p. Tau p is, it was constant for all for frequency 1 and frequency 2. But what we know, any signal as per our Fourier transform, this thing, we know that any signal can be decomposed into any number of sinusoidal signals of having different amplitudes and the frequency components. So herein we have just taken a signal where we are having only two frequencies f1 and f2. But if you take up any of the frequency components in this domain, it would come out to be a, this relationship, it would come out to be a linear filter. Okay, and hence it is called that this FIR filters, they are having a, they are basically a constant phase filter or a linear filter. Okay, So group delay, if you look into the group delay, minus of d theta omega by d omega, what it would be? It would be basically a constant. Right. Now there are certain disadvantages of this filter. What are these disadvantages? There are no specific rules. Okay. So while you are starting to design a filter, it is not possible for you to design a filter with an actual cutoff frequency. It is very difficult to design a FIR filter with actual cutoff frequency, and it has to be a trial and error method. And secondly, the order of the filter of the FIR filters are quite high. It is usually, say, the order is usually 80, 100 or even more. Okay, so order of the FIR filters, they are very high. So actual cutoff frequency, as I told you, it cannot be what do you call this is more of yeah, trial and error method to design a filter with an actual cutoff frequencies, and hence the designing of the FIR filters are by trial and error method. There is one empirical method which is regarded as the Kaiser method for the designing of the filters. However, on the contrary, if you look into the designing of the IR filters, the designing of the IR filters, they are definite, and you already know the cutoff frequencies and all these things beforehand, and accordingly you can design the filters. Okay. Now, what are the filter characteristics? Lastly, the filter characteristics. So we have the order of the filter, FIR filter, they are very high. I already told you that the order of the filters are very high, and since the order of the filter is very high, there is an increased complexity. What type of complexity? There is an increased yeah, mathematical complexity while designing the FIR filters. Okay. Now, coming to the FIR filter designing, as I told you, all the poles, they would be within the center, and we will only have the liberty to place the zeros anywhere on the Z plane to modulate the gain. Okay, so this is because this is the reason you will find in many textbooks, you will find that FIR filters are designed by the placements of the zeros. Okay, because everyone knows that all the poles there at the origin of the Z plane, and you cannot place anywhere, you cannot place the poles anywhere on the Z plane for the FIR filters. Okay, so that does not mean that FIR filters does not have any poles. They have poles, but all the poles, they are within the at the origin of the unit circle. Okay, so there is a filter which is regarded as all pass filter. There is a filter which is regarded as all pass filter. Till now, we have talked about low pass filter, we have talked about high pass filter, we have talked about band pass filter and all the things. But what do you mean by all pass filter? All pass means all the frequency components will be passing. So it is the simplest FIR filter you can design. No zeros, nothing. You just place a pole at the origin, one pole, two pole, whatever poles you want to put. So you design the all pass filter. Why that is all pass filter? Can you tell me? क्या क्या? I didn't get you. थोड़ा जोर से. It is in the gain. Increasing the gain. Just I told you that FIR filters we consider that the gain is 1. देखो देखो इमेज देखो ये जो पोल जीरो प्लॉट है. The answer gives you the thing. This pole zero plot gives you the answer. Basically, what you have to look into a filter if you want to look into the frequency response of the filter. What you want to see from here? What is the important criterion? If you want to look into the frequency response of this filter, so what is that? So if you see the distance of this pole, what is this? Everything is one, right? So that means all the frequency. If you place a frequency, if you place a pole at the origin of a z plane, that means all the frequency components they will be affected equally. Okay, so there will be a multiplication of 1. So there will be no suppression of the signal component. Okay, there will be no suppression of the signal component. You're getting my point? So just placing a pole at the origin of the filter, we'll be having the we'll be getting the all pulse filter. Amplitude response is not getting changed, but that does not mean the phase response will not change. The phase response would be minus of omega t always. Okay, because phase is changing. What is phase? These angles are the phase, right? So the phase would be changing. However, they will be the amplitude response will not be changed. Okay. However, this change in the phase, it is a linear process. So all the frequency components will be affected in a similar way. Okay, and hence there will be no distortion of the signal components, the frequency components. There will be no distortion of the frequency components. Okay. Again, when I talk about these FIR filters, if you look over here, herein capital N, the order of the filter is 3, right? So that was for the sake of our understanding. But just few moments back, what I told you that this N, it is very high, maybe 80, maybe 100, maybe 200, right? And if n is like this, if you see the coefficients you will be dealing with, so here we are having 4 coefficients. One is z independent and other are z dependent. Okay, z inverse dependent delayed components. So we can be dealing maybe up to 200 or maybe even greater number of the filter coefficients, which increases the mathematical complexity of our FIR filter calculation. Okay, if you consider that you want to have a similar kind of response with the FIR filter, IIR filter, the order of the filter would be say 3, 4. At the max, we would go up to 10. Okay, at the max we would go up to 10. Okay, so in the worst case, if you remember, we said the number of the hz, they are regarded by the two polynomials pz by qz. Okay, at the max what we will be having, the coefficients we will be dealing it on the numerator, it will be maybe 10 to 11, In the denominator, we will be having 10 to 11. So the total number of this what you call filter coefficients, it would be maximum of 20. However, usually while we go for the designing of the IR filter and this thing, we hardly go beyond the order of the 3. So you can see the mathematical complexity is much lower in the IAR filter. Even though if you see the method of calculation of those filter coefficients, it would be quite complex. Okay, but the implementation part, it will be bit easier. Okay, now this we have discussed. Now coming to the types of the FIR filter. Coming to the type of the FIR filters, we are having 4 types of filter. The type 1, type 2, type 3, type 4. So we are having the order of the filters and the length of the filters. Okay, so order of the filter, it would be given by capital N, and the length of the filter, it would be given by capital L, which is equal to N plus 1. Why this is so? If you look into the previous equation, the order of the filter, it was 3, but if you look into the coefficients, 1, 2, 3, 4, N plus 1. So similarly over here also, order of the filter and the length of the filter, it would be different. So while you are doing the numerical, you have to be careful whether in the numerical it has been given that you find out the filter which is having an order of 4 or a length of 4. Okay, so this is where we can trick you. Okay, so you have to find out whether the order of the filter has been given or the length of the filter has been given. Okay, now the type 1 and type 2 filters, they are regarded as the symmetric filter. Why they are regarded as the symmetric filter? Because they follow the equation h of n equals to h of capital N minus n. Okay, so let us take the example of the type of a type 1 filter. Let us take the example of the type 1 filter where the order of the filter is even. So here the order of the filter is even 0, 1, 2, 3, 4. Okay, the maximum n value is 4, so length is 5. Now if you see h of 0, the first component, we will start with n, right? We will start with n equals to 0. So h of 0 equals to h of capital N means 4 minus of 0, 4 minus of 0, it is h of 4. So if you see the amplitude value of h0 and h of 4, both are same. Similarly, if we put n equals to 1, its value should be equals to h of 3, and in the middle we will be having h of 2. Okay, so type 1 filter, it will be having odd number of coefficients, and across the middle value, the coefficient value would be symmetric value. Okay, then coming to the type 2 filter, the order of the filter is odd, however the length is even. So we will be having a center point something over here. So again you put h0, it will be h of 5, it would be equal to h of 5. Why? Because the order is 5, 5 minus 0, 5. So h of 0 and h of 5 equal to, they are equal, they are having the same coefficient values. Then h of 1 and h of 4, they will be having same coefficient values, and h of 2 and h of 3, they would be having same coefficient values. Okay, coming to the type 3 filter, they are anti-symmetric value. That means across the middle point, the coefficient value would be just the opposite. Okay, So herein, if you see, the equation is given by h of n is equal to minus of h of capital N minus n. Okay. So h of 0, if you see, it is positive value. H of 4, it is negative value. Again, h of 1 is positive value. This is negative value. This is again, this is the middle point. So there will be no change. Okay. Type 4 filters, again the same thing. H of 0 is equal to minus of h of 5. H of 1 is equal to minus of h of 4, and h of 2 is equal to minus of h of 3. Okay. Usually, you will find that type 1 filters, they are most commonly used because of the ease of implementing the filters, and in some cases type 2 filter. Okay. Type 1 filter, it can be used to design any kind of filters. It can be used to design any kind of filters. Okay. Type 2 filter, it cannot be used to design high pass filters. Okay. Type 3 filters, it cannot be used to design high pass filter and low pass filter. And lastly, type 4 filter, it cannot be used to design low pass filter. Okay. There are mathematical explanations for this, but I am not going into that because it will make our lecture lengthy. Okay. So these are some of the important things which you should keep in mind. Okay. And that is why you will find in many of the, now coming to the realization of the filters. I have taken a very simple example. The HN coefficients, they are given. Now if you see, I have told you how to break this one and get to this equation. Yz equals to this one, it's given. So if you see, the coefficient of xz and z to the power minus 0, which is equals to 1, and xz z to the power minus 4, they are same. Again, this coefficient and this coefficient, they are same, and this is the middle one. So how to implement that in the direct form? X1, just this one, it is coming to yz, then it is being delayed and multiplied by 2, delayed multiplied by 2, added up, added to the output, again coming to this one, delayed multiplied by 3, again added up. Okay. Then again this component, this is delayed multiplied, added up, this one delayed multiplied, added up. Okay. So this is how you implement the direct form, implement the FIR filter by the direct form realization. Okay. Then there is another important thing which is regarded as linear phase in implementation. So over here, you look into this aspect carefully. I have written the same equation. Okay. However, I have taken all the components which are having same coefficient values. Okay. And this is left alone. So okay, now what it is done, xz signal going over there, getting the delay, getting the delay, getting the delay, getting the delay. So initially what we had, one, so one component, it breaks down over here, So it is added up, it is getting multiplied with 1, this one, and x4 delay. So see, the signal component which is coming over here, it is also having a coefficient values of 1. So after all these components are getting added up, then we are having this multiplier. X0 component without delay and XZ components after 4 delays, they are getting added up, and then there is a this multiplication. Okay, then we are having after Z inverse and after Z to the power minus 3. So after Z inverse is this one, we get in an adder, and after minus 3 we are again tapping the output, we are adding up, and then there is a multiplier of 2. This is multiplied. Now these two components, they are added up over here, and lastly 3 multiplied by Z to the power minus 2. After minus 2 we are tapping, multiplied by 3, then again added up to get the yz. So what is happening, we have reduced the multiplication operation significantly over here. Okay, so this is called linear phase implementation. This type of implementation or the realization of the filter is regarded as the linear phase implementation. Okay, so next we are having designing methods. Fourier series method without using window, Fourier series method using window, then Fourier transform method without using window, then Fourier transform method using window. Okay, so this will be uh, studying in the next class, and all these things I will be covering from the book Digital Signal Processing by BS9. Now before going into the filter designing aspects, we need to understand the frequency response of the digital filters. So I will be trying to cover it briefly over here. We have already discussed, but again before starting it, I would like to recap the things. So this is the analog filter omega c you are having, but in the digital domain, if you see 0 to omega c, then 2 pi minus omega c to 2 pi region. This thing, why this is so? Because if you place a filter over here for the low pass filter, so you are having two cutoffs. One is say omega c, and what would be this one? This would be, this point is 2 pi, so 2 pi minus omega c. Now suppose taking this point as the joining point, if you open it up and if you place it as 0 to 2 pi, so see what you will be having, 0 to omega c, you are having the effect of the poles. So we are having a linear response up to omega c. After that, this pole is having no effect up to 2 pi minus omega c, and again from 2 pi minus omega c to 2 pi, you will be having a high response. Okay, but we said that we can also represent it as pi to minus pi, and in that format, if you see, if you put it, we get the components as minus omega c to omega, because what is this? This is nothing but minus of omega c, right? So the filter designing aspects, this thing can be represented either in the 0 to 2 pi or in the minus pi to pi format. And usually what happens is that we go for the next one, minus pi to pi format. Okay, in most of the cases. For the high pass filter, it looks something like this. And what would be its response in the minus pi to pi format? Minus pi to minus omega c, you will be having the high passband region, and omega c to pi. So what does that mean? We are having this z plane, we are having a pole over here. So this pole is having the effect. So this is a omega c, and this would be minus of omega c. Okay, so if you open up minus pi to omega c high, then minus omega c to omega c, it is the stop band, then omega c to pi, again high band. Similarly, if you go for the band reject filter, it would be something in the analog domain, and it would be something like this in the yeah, digital domain. Okay, so why that is so? In the simplest term I am giving it. So high pass filter, band reject means high pass filter and low pass filter would be there, and there would be some stop region. So I'm not plotting any zeros over here. So there would be some zeros in between. So if you look into the region minus pi to minus of omega c by 2, okay, then we get into this region minus of omega c1 to omega c1. A continuous region is there, okay. Then lastly we get omega c into 2 pi, okay. Lastly, band pass filter, it should be something like this. So say for example band pass में, okay. So minus pi to minus omega c2 to minus omega c1, this point high, this point to this point is again 0, again this point to this point omega c1 to omega c2, and then to pi, okay. So why I am showing you this thing, because this limits what limit you will be taking for designing the FIR filter. So over there we have to do some integration. So these limits, understanding of these limits would be important for you to understand how we can design the filters. Okay. So if you see, this is the base equation which we will be using it in our from our next classes. So all of you should have your this calculators ready from the next class onwards. Okay. Thank you. If you have any questions, we can discuss. Mhm. You have not understood. See what we are doing. Initially, what we have done, this and this, they are having same coefficients. We have taken it together. Okay. Then this one and this one, they are having same coefficients. We have clubbed it together. Now what I have done, I have taken, there are 4 z's. So increasing number of z's. So from the midpoint exit, this is the first point, first z inverse, second z inverse, third z inverse, fourth z inverse. The signal is going like this, right? Now here what we have done, directly from the exit, whatever the component is coming, and whatever is coming after the this z inverse or the after 4 delays. So we are taking those and adding up. So we are taking directly the signal which is coming from here, and what is the signal component after 4 delays? After 4 delays, this is the one. So we are added up over here. Okay. After addition, we have a multiplier of 1. So we multiply it over here with 1. Similarly, after z inverse and after z to the minus 3, after z inverse is this one, this point, and z to the minus 3 is this point. We added up the values, then multiplied with 2, and this was after z to the minus 2. After z to the minus 2, we have tapped it, multiplied with 3, and added up everything to get the z by z. Okay. Now suppose there would, it would have been, say, instead of 4, there would the order would be, say for example 5. what you would have done. Again, you have to look into this equation. This Z2 and some other value, they would have been clubbed together. Okay. So from there, you have to take it. You have to look into the scenario, which things you can club. Okay. Anything else?